Okay, thank you. So, okay, so first of all, I would like to thank the organizing committee and program committee for inviting me, and it's really my pleasure to give a talk at the FPSAC. And today I want to talk about something about the Stanley-Reisner rings and triangulated manifolds. And actually, is something? Mute. Okay, thank you. And actually, I originally planned to give a kind of a survey of this topic, but at some point I realized that I'm not good at giving a survey talk, so I somehow changed my mind today. So I basically just took one topic on this, one problem about this topic, and which is a purely a combinatorial problem, but it actually very much related to the Stanley-Reisner theory. And so this is a plan of my talk. So I first talk about one simple combinatorial question about the triangulated manifolds, which is a purely combinatorial question, but it's actually very much related to the Stanley-Reisner ring. And the goal of this talk is to explain how the problem is related to the algebra of the Stanley-Reisner ring. And anyway, so let me first explain some notation. So the main player of this talk is a simplicial complex. So actually, it's abstract simplicial complex, which is actually a collection of some subsets enclosed under the inclusion. And this is actually a very basic object in combinatorial topology. And it is a collection of subsets, but it has some geometric meaning. And indeed, if you identify each subset with simplices, then you may consider that abstract simplicial complex is the union of the simplices. So for example, if we have a set 1, 2, 3, then we can associate the triangle with vertices 1, 2, 3. And if you have a set 1 to 4, then you identify with it with the triangle 1 to 4. And in this way, you can consider that the simplicial complex is a collection of the simplices. And if you take a union of all these simplices, then you get a geometric realization. And what I want to talk about today is a simplicial complex whose geometric realization is a triangulation of a manifold. So let M be a connected topological manifold, and I also assume that it's connected. And then I want to say that the delta is a triangulation of M if its geometric realization is homeomorphic to M. And here is some simple example. So for example, if you consider the torus S1 cross S1, then you can make a torus from the piece of square by identifying these edges like this way. And so if you want to get the triangulation, you just triangle this piece of the square and something like this way. Then you get a triangulation of the torus. So this is kind of a typical example of the triangulation. And about the triangulation, so what I want to discuss today is the following problem. So the question is that how many vertices we need to triangulate a given manifold? So maybe I should explain more precisely. So my question is, what is the smallest number of the vertices which you need to triangulate a given manifold? So for example, as I said, this is a triangulation of a torus, and this actually have 9 vertices if you count correctly, and you need to be careful about the identification. But this is a natural triangulation, but it's not the smallest triangulation. You actually have there is a 7-vertex triangulation with the torus, and so our question is, so what is the smallest possible number of the vertices to triangulate them? And let me try to define the question more precisely. So let Fi delta to be the number of the I-dimensional faces of delta, and for manifold M, let F0 mean to be the minimum of the F0 delta, so among all the triangulation of M. And then you can interpret the question like, so the given a manifold M, so compute this F0 number. This is the question which I want to consider. And here's some simple example. So if you consider the 2-dimensional sphere, you just need 4 vertices to triangulate it, because the tetrahedron is obviously the smallest triangulation of the sphere. And for the RP2, projective plane, you need 6 vertices, and for the torus, you need 7 vertices. So it's not very obvious that these 6 and 7 are, smallest number of the vertices, but it's not very hard to difficult to see. And about this question, we actually know the complete answer for at least the surface case, so 2-dimensional closed manifold. And so actually, there's a class, as many of you know, there's a classification of the closed surfaces, and there are only 2 types of the closed surfaces. So one is the orientable surface of genus G, which is connected sum of G copies of the torus. So if you don't know what is a connected sum, I don't want to explain what is it. But so if you write a picture, so the orientable surface of genus G is just like a donut with G holes, as you actually see yesterday. And the other one is a non-orientable manifold of genus G, which is actually a connected sum of G copies of the projective plane. And triangulation of the surfaces are actually very much studied by the people in graph theory, particularly in connection with the coloring problem. And it was proved by Junjam and Ringel. So if M is a closed surfaces, which is not equal to the orientable manifold of genus 2 or non-orientable manifold of genus 2 or 3, then the smallest possible number of the vertices unity triangle M is given by the smallest F0 satisfying this inequality. So there are 3 exceptions, but for these exceptions, you just need to add +1 to this expected value. So basically, this theorem gives a complete answer to this problem for at least a closed surface case. And here, just an example. If you, I don't want to give an exact computation, but if you apply this inequality, you can easily get if you have a orientable manifold with genus 4, you actually can triangle the 11. The smallest number of the vertices which you need to triangulate is 11, or something like that. And anyway, this is kind of some classical thing. But so if you want to go more, so if you want to study this problem in higher dimension, the problem actually becomes very hard. And maybe some of you feel that so asking this question for the higher dimensional manifold is a crazy question, because of course we don't have a nice classification of the higher dimensional manifold, and also it's in some sense it's very clear that if we have a very complicated manifold, it's definitely impossible to find this number. But actually, the situation is that if M is very, very simple, so we cannot really determine this number. So here I write some examples, so which is known and which is not known. So for example, if you consider the product of 2 spheres, which looks like a very simple object, so if you consider product of 2 spheres, we know the answer for S1 cross SD, which is actually depends on the answer actually depends on the parity. And we also know the answer to S2 times S2 and S2 times cross S3, S3 cross S4, but we do not know the answer to the even for the S2 cross S4. And also, if you consider the product of 3 objects, we don't even know the answer for the 3-dimensional torus case. If you just if you consider the product of 3 circle cases, the answer is not known. I think this number is actually expected to be 15 or something like that, but nobody can prove it. And so there are 2 difficulties to study this problem. So the one difficulty is that if we want to discuss this problem, you actually need a very good lower bound for the number of the vertices which you need. And in the surface case, everything is explained just one inequality, which is actually called the Hilda's inequality. And this equality is actually, in some sense, very easy follows from the Euler's relation. But if you go to the dimension more than 3, so the Euler relation is not really helpful, and you need something else to study this problem. And the other difficulty is that if you want to construct an actual triangulation, it's also a very hard problem. I mean, it's something like that. It's a very technical problem, but construction is also very difficult. So we have two difficulties to this problem. And anyway, so I will not discuss this latter difficulty because I'm not topologist or not combinatorial topologist, so I'm algebraist. But it is known that, so currently we somehow understand that if you want to get a good lower bounds, then we somehow know that the Stanley-Reisner theory, in particular, so some classical result such as upper bound theorem or lower bound theorem is quite useful. And this is what I want to explain today. And before explaining some algebraic parts, I just want to give a result, what we know now. So we somehow now know that this series of the inequality, which is so first proved by Novick and Schwarz for some cases, and eventually, so the general cases followed from the algebra-sheet's hard-rested theorem for the spheres. But this is, it's hard to understand what is the meaning of this inequality, but I just want to say that this is an inequality which somehow generalizes the Hilda inequality. And I forgot to say that beta I is a Bethe number. And if you use this inequality, you can somehow get a F0 mean for the new group of the manifold. So there are some people who try to find this number for using this theorem for certain manifold, for example. So it was shown that if you consider the connected sum of 143, connected sum of the 143 S3 cross S1. Okay, so there are some people who study this F0 mean for certain higher dimensional manifolds. And for example, so if you consider the connected sum of the 143 copies of the S3 cross S1, you need 71 vertices. Or if you take a connected sum of 342 copies of the S3 cross S1, then you get 101. And in three-dimensional case, you need actually the product doesn't really work, and you somehow need a non-orientable object. So this notation means that the three-dimensional Klein bottle. But anyway, so if you take many connected sum, then you can actually compute this number. So some of you may wonder that what are these 143 or 342? But about this question, I would say that there are cases that we actually have. This is an inequality, and the left-hand side, it's very rare that the left-hand side and right-hand side is equal. At least so you have some special cases that we could have an equality for, in certain values of beta 1. That's the reason we get some strange values in here. But anyway, what I want to really say is that in the 1980s or something like before, we can only discuss this problem for the surface case, which is the connected sum of the torus. But we can now improve the situation, and so, for example, and we can somehow treat the connected sum of the S1 cross ST. And this is a kind of a small development, but the big thing is that we can indeed start to handling the higher dimensional objects, and which is not a small development in my opinion. And to obtain this kind of results, we really need commutative algebra Stanley-Reisnering, and that's what I want to explain from now. Is everything okay at this moment? Okay, then now let me give a quick introduction to the Stanley-Reisner ring. And I first want to explain very classical result about the Stanley-Reisner ring of polytopes and spheres. So maybe this is boring part for some of you. But anyway, so let me try. So let delta be a simple complex on the bracket n. And let S be a polynomial ring over the real numbers. So if you prefer, you can replace the real numbers to any field. But I just want to work on the real number just to simplify the notation. And then the Stanley-Reisner ring of a simple complex is a quotient of polynomial ring by the ideal I delta, which is the ideal generated by all square-free monomials, which correspond to non-faces of delta. And here is the example. So if you consider the octahedron, then the minimal non-faces are 1, 2, and 3, 4, and 5, 6, because you don't have an edge between 1 and 2, and you don't have an edge between 3 and 4. So 1, 2, and 3, 4 are the non-faces. And the ideal I delta is generated by x1, x2, and x3, x4, x5, x6, something like that. And I will discuss the Stanley-Reisner ring, but about the simple complex, I mainly discuss the simple polytope, which is a polytope all whose faces are simplices, because this can be naturally identified with a simple complex. And I also want to discuss the simple sphere, which is actually a triangulation of a sphere. And the simple polytope is always a triangulation of the sphere, but the converse is not always true, because not all the triangulation of a sphere has a convex realization. And I want to explain a little bit about why we are considering the Stanley-Reisner ring. And so it somehow often happens that nice combinatorial property of the simple complex somehow comes from the nice algebraic property of the Stanley-Reisner ring. And I actually just want to give two examples. For example, one thing I want to introduce is that if you consider the then-Zamaville equation, which I will explain later, but this somehow comes from the Poincare duality of the algebra. And if you consider the lower bound theorem, which somehow gives a sharp lower bound of the phase number of simple polytopes, this somehow related to the hard left-edge property. And somehow nice combinatorial theorem of the polytope comes from the nice algebraic properties, which this is what I want to explain. And let me first explain what is the then-Zamaville equation. So let P be a simplicity polytopes, and the then-Zamaville equation is a series of the inequality about the phase numbers, so F numbers. And it's hard to get an intuition for what does this inequality means, but I want to say that this inequality describes all the linear relation of the phase numbers. And from this equality, so you can see that if you know the phase numbers from the F0 to F half of D, then it actually determines all the phase numbers. Maybe I should give an example. So for example, if you consider the three-dimensional polytope, and if you suppose that you know the number of the vertices, then the then-Zamaville equation actually in this three-dimensional case tells that F0 minus F1 plus F2 equal 2, which is just the Euler relation. And it also says that 3 times F2 is equal to 2 times F1, which essentially comes from the fact that every triangle has 3 edges, and every edge is contained in 2 triangles. And the then-Zamaville equation is essentially these two equations. But if you use these two equations, so you can somehow write down F1 and F2 just by using F0. So F1 is what happens? F1 is actually 3 times F0 minus 6, and F2 is 2 times F0 minus 4. So if you know the F0, then you can know all the F numbers. And the then-Zamaville equation is just a kind of a generalization of this simple three-dimensional case. So if you know the first half of the phase numbers, then you can know all the phase numbers. And actually, so this Then-Zama equation has a much simpler explanation if you introduce what the people call the H numbers or H vectors. So, and H vector is defined somehow as follows. So let H0 to Hd be the linear combination of these F numbers. So then it's a bit complicated definition, but if you use these numbers, the Then-Zama equation actually is known to be equivalent to the Hi is equal to Hd minus I, which is quite simple inequalities. And if you get this kind of simple equality, so you can somehow expect that this is a kind of a Poincare. This somehow comes from the Poincare duality, and this is indeed the case. And there are some geometric meaning, but I just only explain the algebraic meaning. So now I want to talk a little bit about the commutative algebra. So I want to say that the graded algebra is a Poincare duality algebra of degree d if the top degree is just isomorphic to the one-dimensional vector space, and this multiplication map is non-degenerated for all I. And this is a kind of algebraic generalization of the Poincare duality of the manifold. And if it is not hard to see that if R is a Poincare duality algebra, and if its Hilbert function has this form, then we get Hi is equal to Hd minus I, which is essentially the same equality which I explained about the Then-Zama equation. And so this Poincare duality algebra is about the finite dimensional object, but Stanley-Reisner ring is usually not the zero-dimensional object. So you need some reduction of the Stanley-Reisner ring to the finite dimensional algebra. And this is also standard in commutative algebra, but so it is really well known in commutative algebra that if R is a graded algebra of Krull dimension D, then we can choose a D-linear form theta such that R modulo theta has a Krull dimension 0. Krull dimension 0 means a finite dimensional algebra. And this theta is called the linear system parameter, and R mod theta R is called the Archinean reduction. And the point of this technique is that when you want to study the higher dimensional object, if you take Archinean reduction, then somehow you can associate a finite dimensional algebra in a natural way. But when you do this, we usually need some assumption, which is usually assumed to be the link need to assume to be the Cohen-Macaulay, which means that if for every which means that for every linear system parameter, so any linear system parameter is a regular sequence, which means that each theta I is a non-zero divisor of the R modulo theta 1 to theta I minus 1. And I also want to define one more definition. So I also want to say that if R is Cohen-Macaulay and Archinean reduction is a Poincare duality algebra, then the ring is called Gorenstein. I defined somehow Cohen-Macaulay property and Gorenstein property using the linear system parameter, but there is some homological characterization of these things. And actually, so you can somehow study this object. I can check these conditions somehow homologically. So that's, and you can somehow check how when the ring is Cohen-Macaulay, in particular when Stanley-Reisner case. But I don't want to explain much about the Cohen-Macaulay ring. And anyway, about the Then-Zama education, what I want to say is the following. So let P be a simple complex. Simple D polytope. Then I explained that Then-Zama education says that Hi is equal to Hd minus I. But about this case, it was proved by Stanley that if delta is a Cohen-Macaulay ring, then so R is a Stanley-Reisner ring. The Archinean reduction of the Stanley-Reisner ring, its Hilbert series is given by the H numbers, and it was also proved by the Reisner that if you consider the Stanley-Reisner polytope, it must be Gorenstein, which in particular means that the Archinean reduction must be a Poincare duality algebra. And these two somehow explain that why we get the Then-Zama equation algebraically. So we have if you consider the simple polytope, H vector is its Archinean reduction, and Archinean reduction is a Poincare duality algebra. So it somehow gives an algebraic reason to that we have a then-Zamabil equation. And I want to show one more example, which you can use algebra to explain the combinatorial results. The other one is the upper bound theorem and lower bound theorem. So now let P be a simple D polytope with n vertices. Then the upper bound theorem says that if you consider the phase number of the polytope, it is always bounded above by what we call the cyclic D polytope. And it was also proved by Barnett that the phase number of the simple D polytope is bounded below by what we call the stacked polytope. And I don't want to explain what is cyclic polytope or stacked polytope, but the important point is that you somehow have a sharp lower bound and upper bound of the phase number of the simple polytope by these theorems. And these theorems can be somehow simplified if you use the H numbers. It's known that upper bound theorem actually follows if you can prove that HIP is less than or equal to this binomial quotient. And the lower bound theorem is actually equivalent to saying that H2 is larger than or equal to holds for all simplicial polytopes larger than whose dimension is larger than or equal to 4. And it's a bit tricky that this lower bound theorem and the F version of lower bound theorem and the H version of the lower bound theorem is the same statement, but there is some trick to explain that this H version implies the F version, and actually they are essentially known to be essentially equivalent. And if you consider this lower bound theorem, so you have this actually somehow related to so-called the hard-left theorem. So I just want to explain what is the hard-left theorem. Probably many of you know. So let R be a Poincare duality algebra of so-called degree D, and then I want to say that R satisfies the hard-left property. You just write HL if there is a linear form such that the multiplication of this map from the degree I part to degree D minus I part is bijective for I. And it is somehow well known that if a Poincare duality algebra has a hard-left property, then its Hilbert series is actually symmetric and unimodal, which also, and it's in particular, it's actually also means that if you consider R mod LR, then the Hilbert series can be written as H0 plus H1 minus H0 T plus H2 minus H1 T square with blah, 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 something like this. And the unimodality somehow comes from that these numbers becomes non-negative. And anyway, so by this property, you can actually explain H2 is larger than or equal to H1. It was proved by Stanley that if P is a polytope, and if we choose some natural system parameters, then the Archian reduction of the Stanley-Reisner ring satisfies the hard-left theorem. And this is a kind of a beginning of the Stanley-Reisner ring theory. But anyway, so I just want to summarize. So let P be a simplicial D polytope with n vertices, and then we have an upper bound theorem, which is actually says that the phase number is bounded below by the stacked polytope and bounded above by the cyclic D polytope. And you have a H version of these theorems. And this H version of the theorem somehow follows from the hard-left theorem. So I summarize, so using the hard-left theorem, you can actually prove that HI minus Y is bounded below by 0 and bounded above by these binomial equations. And the proof is somehow trivial once you understand the hard-left theorem. So if R is a Stanley-Reisner ring, and if you take a nice system parameters and left-set elements, then if you consider the R mod theta LR, and if you compare S mod theta LR, then this R is obviously a quotient ring of S, so this is smaller than the right-hand side. But if you just count the dimension, then the middle one is exactly the HI minus 1, and the right one is just binomial equation. So you get this inequality. And this inequality somehow proves that the standard, F version of the upper bound theorem and the lower bound theorem. And it's actually much this statement is much stronger than the original statement, but because this is saying that not just saying that H2 is larger than or equal to H1, it actually tells that H number is unimodal. And I also probably should mention that I somehow use the hardest theorem to prove the upper bound theorem, but so to prove the upper bound theorem, you actually don't need the left set property. So it's enough to assume that the Stanley-Reisner idea is Stanley-Reisner ring is Cohen-Macaulay. But anyway, so as I said, this is kind of a beginning of a Stanley-Reisner theory. So if you have if we have a nice theorem of the polytopes like the then-Zamaville equation where upper bound theorem was a lower bound theorem. But if you consider Stanley-Reisner ring, so the then-Zamaville equation can be somehow realized as a Poincare derivative of Stanley-Reisner idea, and the lower bound theorem somehow comes from the hard left theorem. And we can use somehow algebra to recover and also to generalize these properties. And it has been actually a long open problem, which the hard left theorem is hold for also the simplicial spheres, but it was eventually solved by recently at the Procito. So I'm actually not very sure that which name I should put here, but so the situation is that I Procito first announced a proof, but I think people do not really understand his proof. But some years later, Papadakis and Petrotto really put a really understandable proof. So now I think the expert really thinks that this is true. But anyway, the statement that if delta is a simplicial sphere, then it's Arginian reduction of the Stanley-Reisner ring is known to have a hard left theorem if you take a linear system parameter for sufficiently generic way. So everything. So I just talk about the polytope, but everything is true for the triangulation of spheres. Okay, this is a kind of a quick introduction to the Stanley-Reisner rings, and now I want to talk about the main topic of today, the Stanley-Reisner ring of a triangulated manifold. So in some sense, this kind of so what the situation is that we have a very nice theorems about the spheres and the polytopes in 1980s. But at some point, so probably somehow 15 years ago, we started trying to generalize this result to also a triangulation of closed manifold. And somehow the starting point is, I think, the Edo Schwartz paper about this phase enumeration from spheres and to manifold in 2009. I think this is the starting point of this research. But anyway, so let me explain what is known about the Stanley-Reisner triangulated manifold. And what I talked today is just parallel to what I talked about spheres and manifolds. So about the polytopes, I talked about the then-Zamaville equation, which is a nice symmetry about the phase numbers of the polytopes. But actually, it is known that the then-Zamaville equation can be generalized to a triangulation of any connected closed manifold. And the older result was Cree, who proves that if delta is a triangulation of connected manifolds, a closed manifold, then we have this inequality of Hd minus I is equal to Hi plus something. So plus something is actually an annoying term, but so we essentially have some nice equality of Hi is equal to Hd minus I. And so it takes some time to understand that this inequality also comes from the Poincare duality of the Stanley-Reisner ring, but we now know that this inequality also comes from the Poincare duality of the Stanley-Reisner ring. But I probably, before talking about that, I first should say that if you want to study the Stanley-Reisner ring manifold, we have some difficulties. The difficulty is that the ring is not always Cohen-Macaulay, and in particular, it means that the Arginian reduction is not usually a Poincare duality algebra. So the classical result cannot be directly applied. But on the other hand, it is also known in the 1980s that the ring is called the book-span ring, which I don't want to explain the definition of the book-span, but for Stanley-Reisner ring, book-span just means locally Koema-Kore, and if you consider the manifold, it's locally a sphere, so in some sense, it's not very hard to see that the manifold is a book-span ring. And also, about the book-span ring, it is also known that there is a combinatorial formula of the Hilbert function of the Archinean reduction of the Stanley-Reisner ring, which is called the central formula, which is a bit complicated, but I just want to say that there is a formula of Hilbert function. And so about the Stanley-Reisner ring of manifold, we have some nice conditions. It is book-span, but we have some bad conditions that it's not Koema-Kore, or the Archinean reduction is not Poincare duality algebra. And so it takes some time to how we can study the Stanley-Reisner ring of the triangular manifold, but what we eventually understand is the following. So to explain this, I actually want to introduce one idea which is introduced by Japanese commutative algebra Shiro Goto. So he is actually an expert with a book-span local ring, and he actually introduced the following idea. So let R be a book-span graded algebra. Actually, Goto worked on the local ring, so graded assumption is not appears in Goto's original paper. But so take a book-span ring and take a linear system parameter. So let sigma theta to be the ideal defined by this, to be this ideal. This is the sum of this ideal. So this ideal is the first consider the ideal generated by theta i's, but just remove one theta I. And then take a colon ideal with respect to the theta I. And take sum of all of these. And if you, and let's call this ideal to be the sigma ideal. And I probably should some remarks. So this sigma ideal is a little bit larger than the original, the ideal generated by system parameters. And it is also known that if R is Koema-Kore, then this sigma theta is nothing but the ideal generated by system parameters. And what we know is that so when we consider the book-span algebra, then so Archinean reduction doesn't really usually behave nice, but if you consider the R modulo theta sigma, it actually behaves nice. That's what we understand. I doubt that many of the people are familiar with the commutative algebra, but if you familiar with the commutative algebra, and if you wonder what is this sigma theta, so in commutative algebra, we often consider this kind of a sequence of the maps, and this sigma theta is the kernel of this series of the maps. But I mean, if you don't know the commutative algebra, just forget about this comment. And okay, so and then I can now explain what's the situation. So now consider triangulation of connected closed manifold, and it was first proved by Novik and Schwartz that if M is an orientable, then the Archinean reduction is not the Poincare duality algebra, but if you consider R modulo theta sigma, so R modulo sigma ideal, then this is the Poincare duality algebra. And I probably should mention that this is not the original formulation of the Novik and Schwartz, because in 2009 we don't know what is the sigma ideal, and it somehow appears in the recently. But in any case, essentially the result itself is essentially the same. So I use a formulation of the sigma ideal, but anyways, what I want to say that for manifold, so the classical approach, so taking the Archinean reduction doesn't work, but if you just replace the system parameter to this sigma ideal, then the situation do work. So, and to see that, if you want to see what's the situation, so if you consider this 7-vertex triangulation torus, if you compute the H number, then it's 1, 4, 10, minus 1, something like that, which is not symmetric and which even not non-negative. But if you compute the Hilbert series of this sigma, then you actually get a symmetric Hilbert function. And some of may wonder that, so if this Hilbert function is independent, is combinatorial, but I mean independent of the choice of the system parameter, but this is indeed the case. And as I first remarked that, so as I said, the Hilbert function of the Archian reduction of the Buchsbaum ring is a combinatorial invariant, which is a central formula. So if you want to know the Hilbert function of the R modulo sigma ideal, it suffices somehow to see that the difference between the sigma and the usual system parameter, and the difference is just given by the binomial questions times the Bethe numbers, which has a very simple formula. And from this, we know that the Hilbert function of R modulo sigma ideals, and we know that R modulo sigma ideal is a Poincare divided algebra if M is orientable, and this actually implies a Cris-Den-Zamaville equation. And because I'm Japanese competitive algebra, I also should say that, so I present this result, but this is a kind of a special case of a more general result about the Buchsbaum ring due to Shiro Goto, which is a Japanese competitive algebraist. I just want to say that there's some more, this is a kind of a special case of a general theory. But anyway, so in this way, you can somehow associate a nice Poincare divided algebra from the connected cross manifold. And some of you may wonder that it also has the hard-left theorem, but it is also proved recently by a joint work of Adiprasito and Papadakis and Petroto, which still I think preprint, but anyway, they proved that this R modulo sigma theta satisfies the hard-left theorem for a generic choice of system parameters. So we also have the hard-left property. And okay, I have 5 minutes. And okay, so these are the, in some ways, basic things about the Stanley-Reisner ring with a manifold. So, but the idea is just very simple. So when in the classical case, we just take a Stanley-Reisner ring modulo a linear system parameter. But for the manifold case, we instead of considering the system parameter, we just take a sigma ideal. Then usually it works. So that's what we now understand. And then in the last 5 minutes, I want to go back to the first problem. And I want to explain how this kind of things can be applied to. Okay, sorry, something is missing. But how this can be applied to the smallest number of vertices of a triangulated manifold. And I first want to explain a case manifold with boundary, and then later I want to explain the closed manifold case. And if we use what I explained in the last 2 slides, we can actually show that if delta is a triangulation of a manifold, which is not necessarily closed, then we get this lower bound of the numbers of the vertices of the triangulation. So again, so it's not easy to get an intuition of this inequality, but I just want to give some examples. So if you apply a d equal to 3, I equals to 2, beta 1 is equal to 1 case, you somehow get this inequality, which implies that F0 is larger than or equal to 5. And this somehow explains that if you consider triangulation of many Möbius band, you at least need 5 vertices. And there's indeed a triangulation of Möbius band with 5 vertices, so this somehow determines this number. And of course, so if you just want to study the Möbius band, you don't need any commutative algebra, but I just want to explain that this inequality somehow explains this situation. And if you can also, sorry, I'm very bad at using this tool. So if you want to go higher, you can also go to higher dimensions. So for example, if you consider the solid torus, in this case somehow corresponds to d is equal to 4, I is equal to 2, and beta 1 is equal to 1. And you can see that in such a case, the number of the vertices are at least 7, and which somehow explains that the minimum for the solid torus, we need 7 vertices to triangulate it. And I explained some meaning of this inequality, and the proof of this inequality is somehow very simple. So if you consider the Stanley-Reisner ring and take a linear system parameter, So now we have the following inequality. So R modulus theta R, compare R modulus theta R and S modulus, I'm sorry. So this is theta S, I'm sorry. R modulus theta, R slash theta R, and if you compare S slash theta S, then, so the middle one is clearly smaller than the right one because this is a quotient ring. And we also know that there's an ideal sigma theta. Sigma theta is an ideal of R, so the left-hand side is just a submodule of the middle one. And we have this somehow inequality of the algebra. And if you look at the graded part, then the left-hand side, we get the d to the I times beta I minus 1. And the right-hand side, you get the left-hand side with this claim. And so in this way, you can somehow get the inequality of the number of the vertices. And this is the case of the manifold with boundary. And if you want to go to a closed manifold, you somehow need to take into account the Hard-Lefset theorem. So let me say more. So in the previous statement, I just compared the sigma theta and R modulus theta R and S modulus theta S. But if you want to go to the closed manifold, you always need to somehow take into account the Lefset element, and you need to replace this theta to the theta and Lefset element. And in some sense, and what we now know is the following. So if delta is a triangulation of connected orientable manifold, then there is some ideal J of the R modulus theta and Lefset element such that the vector space dimension of this ideal is d plus 1 to the I of the beta I minus 1. So this is a bit tricky statement, but what I want to say is that, so in the previous slide, the important thing is that, so if you replace R, so in the Cohen-Macaulay case or Polytope case, it's important to consider R modulus theta R. And as I said, if you consider the, manifold, it's very important to think about replace the theta to sigma ideal. And we are looking for somehow the version of the sigma theta ideal of the system parameter plus Lefset element. And we don't have at least I don't have a concrete description, but we somehow know the existence of such an ideal. And this is the ideal J. So this is a version of the sigma ideal of the system parameter plus Lefset element. And using this ideal J, we can somehow prove the result which I explained in the beginning, which is considered to be a generalization of the Hilbert's inequality. But I don't think you need to understand this meaning of this inequality. But what we do is the following. We consider R modulo theta plus Lefset element and S modulo theta plus Lefset element, and then we get the ideal J in the left-hand side. And if you compare the vector space dimension of the left-hand side and right-hand side, you really get the lower bound of the number of the vertices of the triangulated manifold, which was conjectured by Kuhnel. And so this is somehow how we use the Stanley-Reisner theory to get a lower bound of the number of the vertices for triangulated manifold. And so there is some technical part, but I just want to say that everything is just analogous to the lower bound theorem and the upper bound theorem, which is a very classical topic on the Stanley-Reisner. And to study these kinds of things, the important thing is to have a nice version of the lower bound theorem, the upper bound theorem, I think. Okay, so, and I also should say that I use the ideal J, and I say that the ideal J is discovered by myself, but so the original proof is a little more complicated, and this is a simplified version. And here are some future problems. So I just want to put 4, and the first thing is, of course, so it's an interesting question to determine this F0 mean for more manifold. For example, it is open problem that if you consider 3-dimensional torus, we need 15 vertices, and this is, I think this is a conjecture of Kuhnel or someone, and still open problem. And we have some nice Stanley-Reisner theory, but we still couldn't able to prove this kind of thing. And, oh, sorry. And if we want to prove this kind of thing, I think we need to define the upper bound or lower bound theorem. And for the lower bound theorem, we somehow understand what's happening, but we, for example, we don't really understand the upper bounds of the phase number. For example, if we don't even know that what is the maximum of the F2 of the n-vertex triangulation of the S1 cross S3 minus S3. And also, so every result about the manifold using a Stanley-Reisner only considers the Betch numbers, and but if you want to study the torus or something like that, we probably need more refined information. And I think the only result which is not relevant to the Betch number is something is a result of Novik and myself, or I'm sorry again, which somehow give a lower bound in terms of the minimal generator of the number of the generator was fundamental group. And these are some combinatorial, but it's also a question that if we consider the R modulo sigma theta idea with the orientable manifold, it's a Poincare duality algebra, and it satisfies Hardreff's theorem. So it's a natural question, I think. So this somehow comes from the geometric object. I mean, this is some cohomology ring of something. It's a, I think, open question. And okay, so now I want to go to the last session. Thank you for your attention. And
so thank you for your talk. Are there any questions?
I think this is sort of related to something you were saying at the end. For like the upper bound theorem, lower bound theorem for polytopes, something that's nice is that it's the same, we have either the cyclic polytope or the stacked polytope that minimizes or maximizes all of the F vectors at the same time. For these questions about manifolds and triangulations, if we're minimizing the number of vertices, does that also necessarily minimize the number of edges and faces and so on, or are those separate questions for what those would be?
I'm sorry.
So for the question of a manifold and the sort of minimal triangulations, you were just counting the vertices.
Yeah.
But what about if I wanted to minimize the number of edges and faces and so on?
I see. So, okay. So in my experience, usually if you, I mean, this is not always true, but in good situation, if you minimize the number of vertices, it also minimizes the numbers of faces in any dimension. But this is, of course, not always true, but in a good situation, usually,
So it's not a theorem, but
yeah.
So you had this result that from Novik Schwartz, I believe, that said if the manifold is orientable, then you have a PDA. And that's not an if and only if from what I remember from your earlier slides, but is there some dimension where that does become an if and only if?
If and only if what?
If, like you say, look at 5-dimensional or higher, then do you get a PDA if and only if the manifold is orientable?
Oh, it's yes, if you work on the field of characteristic 0. But there's a trick that if you work on the field of characteristic 2, everything is orientable. So this orientability is not a big issue actually for us.
Thank you.
Are there any further questions?
So you mentioned that in some of the higher dimensional manifolds, F0 is not known. Are there like sort of complexity results which say that, let's say if the dimension is high or the genus is high, it's difficult to exactly determine like hard or saying that this inequality is satisfied as NP complete or something like that?
So your question is that in higher dimension it is?
Because you had like, in your initial examples, you had S1 cross S1 cross S1, and you said this is not known. And then some other examples where it's not known. So I guess a general question is, are there like some sort of computational complexity results saying that, okay, if this quantity is high, it's hard to exactly determine what it is?
Yeah. So I'm not sure I understand the question correctly, but in higher dimensional manifold, it's really hard to compute the exact numbers of the F0 mean. Is this what you want to? I'm sorry.
Okay, there's another question.
Yeah, wonderful talk. Are there infinite sets of examples of triangulations minimizing the numbers, like cyclic polytopes are optimal and stacked polytopes are optimal? Are there similar constructions that would give minimal examples for an infinite set?
Okay, it's a good question. So yes, we have a similar construction for the S1 cross ST minus 1 for the lower bound. For the lower bound, in some sense, we know such example. But upper bound, we don't know. So it's actually an open problem. And actually, I think I showed you in my previous slide that we don't know what is a maximum of the F2 for the S1 cross S3. So for the upper bound, we don't have a good class. So I think it's an interesting problem.
So I would like to suggest that further questions are postponed to the break. And we thank the speaker again.